אוקיי, ערב טוב לכולם, תודה למי שצטרף לנו לוובינר הטרנס-אטלנטי שלנו. אנחנו מאוד גאים ושמחים לארח פה הערב את רוב ריצ'רסון, מומחה בינלאומי לדאטה, סופר ומרצה מבוקש בכנסים בינלאומיים, וכמו שאוהב לכנות את עצמו, Developer Evangelist בסינגל סטור. קצת housekeeping לפני שנתחיל, יש פה אפשרות בזמן הוובינר לשאיר שאלות או בצ'אט, או לבקש, ואנחנו נוכל לאפשר גם לשאלות תוך כדי ההרצאה בקול, אז תרגישו חופשיים. כמו שכתבנו באג'נדה, הרוב מתחלק לשניים, ההרצאה הראשונה היא הרצאתו של רוב, לאחר מכן איליה ה-CTO שלנו ירצה כאן בערך מאזור 27 עד השעה 7, ואז יהיה גם זמן כמובן לשאלות ול-Q&A. אז without further ado, Rob, the stage is yours.
Very nice. Thank you for the introduction. Hebrew is such a beautiful language, and I wish I knew more of it, but unfortunately, I'll be presenting in English. Thanks for the introduction. I'm a developer evangelist for Single Store. I'm Rob Richardson. Here's the part where I tell you I'm definitely going to post the slides on my site tonight, and they won't be there. I've been that guy chasing the developer, and I don't like it either. So head out to robrich.org, and you'll get to this site. Click on presentations at the top, and here's databases in the microservices world. Here's the slides. They are online right now. Thanks for the introduction. Some of the things that I've done recently. I'm a Microsoft MVP, a data expert. I'm a friend of Redgate, a database company. And I also work with AZ Gift Camp. AZ Gift Camp brings volunteer developers together with charities who otherwise couldn't afford software services. We start building free software for them Friday after work. Sunday afternoon, we deliver that completed software back to the charities. Sleep is optional, caffeine provided. If you're in Arizona, come join us for the next AZ Give Camp. Or if you'd like a Give Camp here in Israel, hit me up on email or Twitter, and let's get philanthropy installed in your neighborhood as well. Some of the other things that I've done, SQL Server Source Control Basics, mine is Chapter 8. And one of the things I'm particularly proud of, I replied to a .NET Rocks podcast episode. They read my comment on the air, and they sent me a mug. Woohoo! So there's my claim to fame. So let's jump into databases in the microservices world. Why do we keep refactoring our applications into microservices, but then we default to the same monolith database that we used before? Let's unpack that and get a feel for application architecture and database architecture in this new microservices world. As we've started developing applications, we've kind of moved from this spaghetti architecture to a ravioli architect to a lasagna architecture, and finally to a ravioli architecture. In spaghetti, we were just copying and pasting the big mess. In lasagna architecture, we start separating things into tiers. Maybe we have our data access tier and our business tier and our front end tier. As we move towards microservices, we have small pieces of functionality that do specific tasks, and we arrange them together into one dish. Spaghetti to lasagna to ravioli. Ravioli, the microservices, is where we are right now, and containers have really powered that to make it really easy. On the left, we have a monolithic architecture. On the right, we have microservices. On the left, it was wonderful where we could deploy all of the pieces together. We contained this application, and we did this because deployment was hard. Well, pardon me. As deployment got easier, as we had containers that could easily deploy our applications, we moved to the system on the right, where containers can call other containers, and we end up with this mechanism of microservices that allows us to easily replace pieces of our application. One of the tenets of microservices is right here, that a microservice owns its own data source. So as we're calling from one microservice to another, we need to make sure not to call from one microservice into another data source. Well, here's what we want. We want this microservice owning its own data. Microservice, it does one small job. It's easy to deploy, usually with containers. We can scale independently of other content, and it's easy to replace. And one of the big tenets of microservices, it owns its own data. Now, it owns its own data because if we ever want to change that data source, we don't need to go audit the entire application and contact every other team. We know that this is the only service that consumes that data source, so we can evolve it as we need to, as rapidly as we evolve our application. A principal construct of microservices is it owns its own data source. Yet usually when we get here, we get to something like this, where we have lots of microservices, but they all depend on a single monolithic database. Oops. I've been guilty of this as well. Why do we get here? Well, the first obvious answer is because the DBA said no. Yeah, the DBA's job is to install and configure and secure the database to protect it from abuse and from downtime. And that's interesting, but really what we want to do is facilitate user experiences. Provisioning a database is hard, and the DBA is worried that if we have too many little databases, one might slip through the cracks. Did we remember to secure it? Did we remember to back it up? It's really unfortunate when we learn that we went to go replace a microservice and we accidentally truncated the database, and then we go to the DBA and say, hey, can you restore last night's backup of, and he says, well, what database? Oops. Yes. To be able to move to an object owning its own database, we need to have databases that enroll in security mechanisms to ensure that authentication is provided for and that we can rotate keys. And we also need to enroll them in backup mechanisms so that we can assure that the content will be secure. So if we don't have a database for each microservice, we can start to simulate that in our application with bounded context. A bounded context is that portion of the database specific to a particular microservice. So if we look at a shopping cart-like experience, what's the bounded context associated with a shopping cart? Well, we need a list of products. We need that product catalog. Now, we're not going to change that, so we just need a read-only view of the product catalog, but we need to be able to get the products, their descriptions, their images, and then we need to be able to create orders. That's it. Read-only view of the product catalog and a write view, a create view to creating orders. By comparison, the fulfillment system. Fulfillment system doesn't need to look at the product catalog at all. For the most part, their only worry is what is the product ID. They do need to be able to update the order status from placed to shipped, but that's it. They have very different bounded contexts. And if we have a monolithic database, we can use these bounded contexts to be able to start to think in microservices. Once we get to the part where we have enough automation to be able to build micro databases, then we can build out a service with its own data. Micro databases. A micro database is that piece of data storage specific to one microservice. Now, to get micro databases, we need to have that automation. We need to have the ability to automatically provision a database. We need to have the ability to automatically secure that database with authentication. And we need to enroll that database in backup services. If we can do that, securing the database and backing up the database, then we can get to this view of micro databases. If we can't get to this view, we can use bounded context, but this is definitely the goal. Lots of different databases. Well, now we have lots of little data stores. Each micro database is owned by exactly one microservice, and other microservices can call into this microservice to be able to get at the data in its data store. Well, there's a few challenges that we may need to look at. How do we do joins? Do I really have to loop through all of the customer records and call the get by ID on that other microservice to get at it? Well, probably not. What we can do is we can create an enterprise service bus that will publish changes to each microdatabase. Now that service bus will span across all of the microservices. Each microservice can publish its events, and those microservices that need to can subscribe to those events. For example, in our shopping cart example, when a user creates a new order, we can publish an event noting the order, maybe it's order content, or maybe just a pointer back to the content that we need. Now the receiving thing, the fulfillment service, can subscribe to that enterprise service bus and grab the details that it needs. Our monthly report can subscribe to that as well. When we need to do these joins, we already have the data that we need because we subscribe to it from the enterprise service bus. At this point, maybe some of the microservices will have no UI at all. They will just listen for messages and compile aggregate views. Another mechanism, who owns the customer record? Should the shopping cart own the customer record? They're creating orders. Should billing own the customer record? They probably have sensitive information like credit card numbers. Or human resources. Human resources is good at keeping secrets. They should definitely own the customer record, right? Or maybe sales. When we have a lead or a prospect, sales is the first person to see it. But there is a difference between a lead or a prospect and a customer. For a customer to be able to place an order, we need a full customer name, we need a shipping address, we need a credit card, and a lead may just be their name and phone number. Maybe that's all I got on the back of their business card. So who owns the customer record? Well, none of them. Let's create a new microservice whose job it is to own the customer primary key and the customer account number. We call this microservice and we say, I would like a new customer number. Pass in the account number and get that customer ID. That customer service is responsible for those two pieces of data, and that's it. All of these other systems have foreign keys off to that service. The shopping cart has a foreign key off to the customer ID. The billing has a foreign key off to the customer ID. And each service now has a foreign key off to this other microservices data. When it comes time to create a new customer, the sales account can call into that customer service and do what it needs to do. Now that customer microservice has its bare minimum. Inside billing, we may have a customer profile that is specific to the billing details. Maybe that's where the credit card number is found, or maybe that's the token off to the credit card processing system. HR has a foreign key off to the customer record and its own customer profile that includes information specific to HR. We have multiple customer profiles, and these customer profiles are specific to the tasks that we're doing here. So now we have micro databases. We were able to enroll it in authentication and backup, and we have enough automation to pull this off. Each micro database is owned by exactly one microservice, and that microservice is the only thing connecting to that database. When we need to evolve that database, we only need to check with that microservice. We don't need to audit the entire system and communicate between departments. That micro database is owned by that service. And what's interesting, now that we have lots of little databases, maybe they don't need to be the same type. Maybe we can pick a data store, even a database vendor, that is specific to the task at hand. I like this quote, said by me right now. So let's take a look at the various database types. Since we have lots of little databases, maybe we can choose a database type that is more specific to the task at hand. Let's look at relational, document, graph, key value, time series, search, object, column store, and you may not have seen this before, NewSQL. Let's take a look at each type, see when's the best use case to use it, and get some search terms that might get us to different databases with this type. We'll also talk about hybrid databases. So first up, as we look at each database, we're going to look at the characteristics of each database. What are the pros and cons, the best use cases, and some examples. Our first one is a SQL database, a relational database. We can think of this as Excel spreadsheets. With each Excel spreadsheet, we have columns, and all of the data in each column is of the same type. If I have a country, then all of the columns, all of the rows in this column, all of the cells in this column are a country. If I have an account balance, all of the cells in this column are account balances. And then I have rows, one row per piece of data. I have a really elegant SQL query language that allows me to query interesting things. As I have related data, maybe I have an order header and order line items, I'll separate this into a normalized structure. One table for the order header, one for the order details. The SQL query language is really elegant in that it allows us to do really powerful things and has been tuned for quite some time. One of the principal things in SQL databases is ACID compliance: atomic, consistent, isolated, and durable. As you grab these slides from robrich.org, feel free to click through into these purple links to get more details about that particular topic. Here in ACID compliance, we know that either the entire content will succeed or fail together. We won't get partial transactions. By comparison, there's eventual consistency. In eventual consistency, it will eventually work out, but we may not have the right answer right now. Think about placing an order on Amazon or buying an airline ticket. When we go to Amazon, we go place an order and they say, thanks for your order. But that's not all. If we go check our credit card bill after getting something at the store, the charge may not be right there on the credit card bill right now. But by the end of the month, we'll have our final credit card bill. Eventually, Amazon will tell us that our package is shipped and we'll be able to do the things. Eventually, the data is consistent. But if we write and then immediately read, we'll probably get the wrong answer. One of the things about SQL is that it is very ACID compliant. We will always get the right answer straight away. The SQL query engine is also really tuned for generations to ensure that it's really fast and compatible. Data storage and data querying have somewhat evolved separately and together to ensure that this is a really powerful and fast way to go. On the downside, it is optimized for storage size. Third normal form means that we can separate our data to store it better. And storage may not be a concern right now that we have terabytes and gigabytes of data at our fingertips. Generally, these databases were built in a previous era, and so they're not designed to scale horizontally. When we scale a SQL database, we get a bigger box. Eventually, we may run out of a bigger box or budget to be able to buy a new SQL database. So SQL databases. Here are some examples of SQL databases. And as you're looking for a database like this, you could probably default to this. If you have a monolithic database, it's probably a SQL database. Next up, let's look at NoSQL databases, or we'll call them document databases. In a document database, we have a piece of JSON. Now, the cool thing is that this JSON is, well, nested. In this case, we have a list of favorites. In a relational database, we couldn't have multiple values in a single cell. Document databases are newer and they're generally distributed. We have lots of machines, so they'll scale horizontally really well. On the upside, I don't have schema that I need to worry about. On the downside, well, my application probably assumes the schema, so I have to put in a lot of logic to say, did I get a blank value and how do I compensate for that? On the upside, we can scale really easily because we can scale horizontally. On the downside, we have eventual consistency, so we have to hope that it works out well. Document databases are great for mechanisms where I need all of the data in one place. Maybe I have a news site or a product catalog, and I need to, given a URL, given a single key, grab all of the details associated with that article. The title, the author, the content, maybe the first page of comments, maybe links to all the pictures. I need all of that in one database query. Graph databases. Graph databases are great for identifying relationships between things. I have both nodes, objects, and relationships between them. I have an elegant mechanism here where I can query by traversing the relationships. Graph databases, how is this different from a relational database with a relational table with 2 foreign keys? Well, it's the query syntax. That query syntax makes it really easy to dive into this mechanism. On the upside, with graph databases, I have this really elegant mechanism to traverse relationships. On the downside, we've optimized for that and left some other things on the table. So I can't really do joins in graph databases. Graph databases are best for social networks and messaging apps, places where relationships are really key. Next up, key value data stores. If we're thinking about this in SQL terms, we can think of a table with 2 columns. One column that is a key and one column that is a value, a binary opaque blob. The beauty of a key value database is that the data in each row doesn't need to be the same. Maybe some data is a JSON object and some is a single value. Now this is cool for get by ID things, where I can grab the content from that ID and run it through. It's not great if I need to query by any other value, because basically the way I would query by any other value is to loop through all of the records, deserializing it in the way that makes sense, and searching through that object in another store. So key value databases are great for cache and configuration, maybe user session data, where I know that I'm only going to query by ID. A key value database, each value doesn't need to be the same. So maybe some of them are JSON, some of them are binary blobs, and the application that reads that key knows how to deserialize that value in the correct way. Next up, time series databases. Here's an example query of querying a time series database. What's interesting about time series databases is that typically when we do a query like this, we get one value in each cell. In a time series database with window bucketing like this, I get a range of values that match that time bucket. In this case, we're looking for the time buckets for a few seconds. So now that I have many values, I can do interesting things like min, max, average, sum. Time series is a great mechanism for being able to process really fast moving data, lots of events. The windowing functions allow me to aggregate across a series of events within a time bucket. This is great for normalizing and smearing across missing or inaccurate values, and to be able to find aggregates within that bucket. On the downside, we've optimized for those windowing functions, and so it's really not a great data store for generic uses. Time series. Here's some examples of time series databases. It's great for when I have lots of real-time data. Maybe I'm tracking mobile devices or IoT sensors, stock trades, or click streams. These are best for time series data when the time is really the critical element in this content. Text search databases. Text search databases are focused on querying for text. Do I have a match in this document? Or what page is the match for this text in this document? We use an inverted index where I'll take all of the words in my document and I'll index them. We can think of this much like the index in the back of a book. So here in a text search database, we're finding which documents have this matching phrase, or where in this document is this matching phrase. They're really geared for that task. On the downside, we don't have relationships and stop words. Stop words. In English, we have un, the, of. These words may not have any inherent meaning on their own, and they're really frequent. So maybe we just won't index them. But if we're in another language, perhaps they're very critical, or perhaps they're different. As we pick stop words, we will likely pick stop words that are both language and culturally specific. And, well, that may get us into trouble. As we're building text search databases, we need to be very careful of stop words. Text search databases are only built for text, and so they're great for searching documents, but not great for other things. Here's some example of text search databases. Text search is based for finding which documents have this phrase or where in this document is this phrase. Object blob stores. We can think of object stores roughly like a file system. Amazon S3 is a great example here. Now, we have a key that we may delimit with slashes to pretend it's a path, and we have a value, a big binary blob. In these object blob stores, we can upload anything, maybe videos, log files, backup files, big content. And the object blob store will store that just fine. On the downside, we can really only query by ID, that key. If we want to do something like loop through all the documents, we need to, well, grab each one, deserialize it using the value that we know how to do. Maybe we need to untar the file and then search through the file there. Blob stores are not great for search by metadata. So maybe we'll have a related index that might give us that contextual information. Maybe that's stored in a relational data store. Object stores. Object stores are great for very big files. They're not great for random access through those files, so we may need a parallel index to filter out just the documents that match maybe this topic or this genre. Column stores. Column stores are really elegant. It's a derivation of a relational database that focuses on data stored in columns instead of rows. On the left, we have a traditional relational database where all of the data is stored in rows. In a column store, they're stored differently. They're stored in column segments. Let's take, for example, country code. Now, we only have a certain number of countries in the world, so if we want to index by country, then we'll have very few values. That means that we can compress this data quite a bit. And when we want to get to a certain country, we can just cruise down that index to exactly that country and start bulk reading from there on. Column stores are great for analytics because we can compress our data so much and get really elegant performance that way. On the downside, column stores are not great for random reads and writes because, well, for the most part, once we get to that spot, we now need to, well, unpack that row. Column stores are perfect for operational analytics. So if I'm doing analytics, a column store is a great choice. If I'm doing transactional data, I may choose a row store to get better performance. NewSQL. As we start looking at NewSQL databases, we'll see that it is, well, SQL plus an SLA. In a NewSQL database, we still have the ACID compliance and relational characteristics of a traditional relational SQL database, but we're distributed. And with distributed, we now are able to scale up a lot cheaper. Instead of buying a bigger and bigger box, we add more boxes. Now, in this example, we have a single store database where we have a main aggregator and a child aggregator. These aggregators will accept client queries. They'll distribute it to all of the leaf nodes that have the data stored in various partitions. Each leaf node will query the partitions that it's responsible for and return those results back to the aggregator, who can use that to form a deterministic query. If we want to get more horsepower from our database, we add more aggregators and more leaf nodes. We can scale up with commodity hardware. With a NewSQL database, we have all of the benefits of a traditional SQL database, ACID compliance, relations, SQL, without the downside of the vertical only scaling. NewSQL databases are great for scaling horizontally while still preserving the SQL aspects. NewSQL databases, they're much cheaper to scale. On the downside, if we need to do a join, we may need to move data across the network. Now, these boxes are on the same LAN. They're probably connected with gigabit or 10 gigabit connections. And so probably that network latency is not a big deal. But that's one thing to consider as you're looking at NewSQL databases. So NewSQL databases. When you've reached that spot where you can't scale your SQL database anymore, or if you're looking to do a lot of really fast data, a NewSQL database can be a really good choice. Hybrid databases. As we look at databases, we may say, well, my application or my data store does this and it does that too. A lot of data stores are moving in the way of hybrid databases. Let me add a JSON data type column so that I can do document data store in the middle of my SQL database. Or I've got a SQL database, but I can also do time bucketing. Single store is a great example of a hybrid database in that it can do time series data, it can do SQL data, it can do NoSQL data, it can do graph data. All of these workloads work really well in single store as a great hybrid database. Here's the money shot. Here's where you want to grab the camera. Here's a list of all of the database types that we've looked at, a brief description, and when this is the best choice. As you start looking at this, if you have an operation where you have enough automation to be able to enroll your databases in authentication and backup, then you can start to choose different vendors for these different data stores. If you don't have that automation, you can use a bounded context to start to get at this data in really elegant ways. We moved from monolith to microservices once we had that database automation in place. With that database automation, we can choose different vendors, or we can choose a hybrid database that includes lots of different features. Micro databases. There's lots of different types, and as you get to micro databases, you may be able to choose a different type of data store better tuned to your problem. If you're looking through this list and you don't find a really good fit, then falling back to a relational database is probably a good move. Relational is a good default. But if you find a problem that exactly matches one of these solutions, a different data store might be a great solution for you. Here's my recommendations. Another money shot to grab your camera. Ideally, you'll use a database as a service. The benefit of using a public cloud for your data store is that you've outsourced the backup and recovery, the uptime. They need to worry about getting your data back if anything happens, and that's a really comforting thing to be able to outsource that. Use automation if you're going to use more than one database server. Provisioning database servers is hard, and having that automation, the Terraform scripts or the cloud scripts to be able to provision these data stores is a really, really elegant solution. Choose a SQL database by default. ACID compliance is really helpful, and the SQL query engine has been tuned for a really long time to be very performant. Choose others if you have a perfect match with the things that they do well. If you have large database blobs, go for an object store like Amazon S3. If you need graph data, find a database that has graph environments. And if you have some things where you need a little bit of these features, use a hybrid data store that allows you to grab the majority of the SQL features that you need and a little bit of these hybrid features. This has been really fun getting to show the different data stores involved in building out a good data architecture. For those who are watching this video later, you can hit me up on Twitter at Rob_Rich. For those who are watching live, what are your questions and thoughts about picking data stores, about automating your database, and about choosing the database that matches your particular need? What are your thoughts? I have a question here. How do you manage disaster recovery with micro database technology? E.g., how do you bring the system to a consistent state across micro databases in a manageable manner? Good question. How do you get to that consistent state, that point-in-time recovery across lots of databases? That's where automation is key. If you have the automation to be able to back up and restore and enroll your databases in authentication, then you can push the button and have it distribute to all the data stores to restore them to that point in time. What I often find, though, is it isn't that all of the databases fail, but rather one microservice was misbehaving. At that point, I probably only need to restore that one micro database, and then the rest of the system continues on. I don't need to plow the entire field just to get that one table back into place. I can just grab that one micro database, restore it into place, and correct the error. Great question, thank you. How do you manage efficient large-scale analytics across micro databases? Great question. If I need large-scale analytics, I'll probably use a enterprise service bus, maybe Kafka, to publish data from one micro database to another, so that then when I need to do that large-scale analytics, all my data is in one place. Alternatively, I can use a single monolithic database and bounded context to be able to carve out portions of that database. Then my large analytics can all function on a single data store. Great question, thank you. Where can we find the presentation? Head out to robrich.org, click on presentations, and you can grab this presentation right there in the list. These are some great questions. Thanks for these. What other questions do you have about micro databases?
Hi guys, thank you very much, Rob. It was very interesting and very useful and very inspiring. Now we will continue with the second part, which will be dive into the single store database. We need another.
Single store has such a great database. I'm looking forward to this. It'll be so much fun.
Yeah, we have some small technical issue here for loading the presentation. It will be ready in half a minute or so. So if you guys have more questions, it's a good time. Also, we can think about questions for the end, and we can try to answer it together, Rob and myself. Yeah, so before my presentation is loading to the site, it will take some time. So a little bit about us and about myself. So I'm Ilya Gulman, CTO of Twingo, and I have some 15 years of experience in this field. Okay, I think we have the presentation. Just a second. Preview. Start. Okay. Okay, good. Good. So what we are going to do here is actually to talk about single store. And I have as a goal that you will come with a clear understanding when you should use it and when you should not. So we will see the architecture, the main use cases, and the short demo of single store database. Okay. So about us, I've already said. A few words about Twingo. So as Twingo, we are a leading big data company in Israel, about 40 experts in a big data area. We have done almost 100 projects, all of those only with big data technologies, plenty of technologies, databases, Spark, whatever you have in this area. We also represent and we have a very deep knowledge in the following technologies like Vertica, MicroStrategy, Single Store, Absolver, Varada, Looker. We are a gold partner, advanced partner of AWS and of Azure. Okay, so in all those areas, we have a good specialized. Okay, in one word, we work with, I think we work with the most interesting companies in Israel and the world. You can see here some of them, like Tabula, Outbrain, Playtika, Monday.com, Kensho, and many others. And that's it about Twingo. We will start with Single Store. Okay, so just about 2 months ago, Single Store was called MemSQL, and they changed the name to Single Store. And this is done in order to say the product has changed. And the vision of the product and the way it works right now, it is a single store, like a one unified place to keep data. And it can work with a variety of cases with different scenarios. So first of all, it falls to category of new SQL databases, which Rob talked about. Okay. Second thing which is unique about it, it is the way the data is stored inside, and we will dive to it a bit deeper today, is built to be able to support both analytical workloads and also OLTP workloads, like small transactions. It can work as a column store, it can work with JSON, it can work as key value, and it can work with text, with Lucene index. So it's a multi-paradigm database. Okay, it's actually most of the database today are very specialized, and this one is very wide and has a variety of use cases. And it was built in from the beginning, from day one, for very fast ingestion. And when I'm talking about fast, it's millions of rows per second. We will have example here. Okay, so two things which I have to mention here. I try to distinguish between this solution and other solutions that we have in this area. First is that this database, on the one side is column store, on the other side it has a row locking and option to work with the small transactions. So it has both advantages of fast analytics and of small transactions in the same place. Okay, and in addition to it, the fast query engine, it means that this query engine is really fast. And actually, any database will tell you that they are fast. Like Presto will tell you they are fast, and Vertex will tell you they are fast. And in any database you work with, they will tell you that they are fast. But this one is a bit different. It is faster than others. I mean that the queries can be as fast as 1 millisecond queries and lower in some cases. And it can also be a long queries running on trillions of rows. So it is fitting for both of use cases. For high concurrency, like we need, for example, you need to process 1,000 of queries per second, 10,000 of queries per second, and each query will do some analytics. It is possible to do with single store. Okay, like other databases also will say we are also column store, etc. But it will be very difficult to find a column store database which can process thousands of queries per second. This is a unique for single store. Okay, so now let's look a bit what can we do with it. What is a single store? Like what are the use cases where it is good, where it is less good? Okay, so in the middle we have actually MemSQL and single store is the same. Okay, it's a different name for the same product. So in the middle we have this database, and single store is a database. Okay, this database from outside actually looks like MySQL. You have a regular SQL syntax, but only from outside. From inside it's something different, and we will see it soon. You can ingest data as you ingest in MySQL. Okay, we're using inserts, updates, but also we have pipelines, which is built in a single store. This pipeline can connect to a source like Kafka or S3 in Amazon or Google Storage or Azure Storage and different others. And it can automatically ingest the data as the data arrives. The most common example is the Kafka. So you have a topic in Kafka. It can be in different formats, in case of JSON or Avro or just delimited and etc. And the pipeline will work with micro batches, ingestion data from Kafka to single store, from topic to table. It can also split it inside from topic to several tables and etc. Can do things in the middle. This is the ingestion part. So we can have a very fast data ingestion, millions of rows per second. Okay, after the data is inside, you can run on this data analytics. You can also run simple transactions. Transactions, relational database, it's also an option. But the fastest will be to run analytics. So you can run dashboards or ad hoc queries. Because it is column stores, it is generally fit to any ad hoc queries you didn't prepare in advance. Of course, it can be used for machine learning, for real-time decision systems, and etc. Okay. The data inside can be of different types. It can be relational data of tables, and you can use joins, and those joins you will surprisingly find that they are fast, even on big scale. You have a geospatial data and geospatial functions. Time series, it can work completely as time series database. You can put JSONs inside. You can use it as a key value store, and you can use it as for text search because there is a built-in Lucene index inside. Okay, so for this database, and where can you deploy it? You can deploy it on premise, either on physical machines or on VMs. There is an operator for Kubernetes, a very battle-proven operator, very good. And you can deploy it on cloud, either on VMs or there is a managed solution, okay, completely managed. Okay, now let's talk a bit about architecture, how the database is built from inside. So from outside, we thought that it looks like MySQL, but from inside, it's completely different picture. Okay, it's built of two layers. There is a layer of aggregators and layer of leaf nodes. Those leaf nodes are the worker nodes. They actually do the majority of the work. They do the filtering, they do the joins, they do the aggregations, and then they transfer the results to aggregator nodes, and aggregator node combines the results together and gives results to the client. The client just talking to aggregator. The aggregators are talking to the leaf nodes. Of course, all the nodes here are redundant. So you can, any one of those can be dead, whatever happens, and the system will be still alive for both queries and for inserts and for everything. Okay, so each piece of data kept at least twice. Okay. Now I want to dive a bit to the storage, which is very, very, let's say, unusual and very, very special in single store. Okay, let's dive here. So originally in single store, when you create a table, you can have two types of tables. There is a row table and there is a column store table. Okay, the row table is completely in memory. It can be indexed, of course, and it is sharded between many nodes, and it is for very fast in-memory processing. Very, very fast in memory processing, including, of course, whatever you can do, inserts, updates, joins, and whatever you wish to do with it. And of course, they are both completely ACID and atomic. So even this in-memory table is backed up by disk. So nothing is lost if system is shutting down in the middle. Okay, but the more interesting part is this right side, this column store, which actually transformed to single store. Single store table has inside the majority of the data will sit in column store format, which will be amazing for analytics. And the newer data will sit in row store format. But this row store format will be very efficient. It will have indexes, it will have sharding, and it is not just some data in memory, it will be data optimized for memory, for indexes optimized in memory. And so for those single store tables, you can have a newer data will automatically be in memory, and the older will be in column store. From your side as an application developer, you will just work with one table. You can insert, delete, update, or do queries on this table. But inside, it will, in a smart way, manage what to keep in memory and what on disk, what to keep in row store, what to keep in column store. Okay, this is something unique to single store. And those tables, the column tables, they will have row-level locking. Okay, so there are many column store databases, Redshift, Vertica, and many, many others, actually. And many of them are good databases, but none of them has row-level locking. And they always, column store database always say, okay, you work with column store, please don't do small operations, don't do the updates, don't do. Here there is no problem. You can work with small transactions or with big transactions, with small operations or big operations on the same table, which is unique. Next. So this maybe is the part which I like the most is the secret. The secret behind the speed of single store. So we did a lot of tests and a lot of POCs comparing single store to different technologies, starting from Druid and actually many databases. And in all use cases which I've seen, on the same hardware, single store was faster. And why it was faster, why it works faster? Because of the way it's built inside. It's built inside in a very efficient way. From the beginning, it was built to use the microprocessor architecture of Intel microprocessors. It used what is called single instruction multiple data processing. It's vectorized processing. And it is natively using AVX 512 instructions. What means, what is behind it is in one click of CPU, in one tick of CPU, it will actually perform many operations. So the CPU has like several gigahertz of operations per second, and usually in one operation, one thing happens. But here in one operation, many things will happen because of vectorized processing. Sometimes 10 things can happen at the same time in the same tick, and etc. So this will just work with CPU with much significantly more efficient way than the regular way people are using. And it's not written in Java, it's written in C++, especially designed for extremely well usage of CPU. Okay, and here is an example. The example you can click on this link later to read the full text. It's, for example, it was able to scan 1 trillion rows per second. It's on 14 machines, but still 1 trillion rows per second to scan in a brute force is very fast. It is a very fast scan. Okay, and it is because of this vectorized processing. Okay, data ingestion. The data ingestion, there are two properties of it. One property is that the ingestion is transactional, it is ACID. Second, it is not creating any locks for reads. So ingesting data will never keep the other queries from waiting. Okay, if we plan the resources in the correct way. And there is a pipeline, as I mentioned before, from Kafka and etc. So just to give you some numbers, and those numbers are like big numbers. So the fastest system for MemSQL was suggesting 10 million rows per second. I have seen personally a system which ingested 3 million rows per second constantly, all the time, with the queries, 3 million rows per second. So if you see how many rows you can actually ingest per day, this is this red number, it's 864 billion rows per day, which is huge. It's very fast ingestion. Many databases will tell that they have fast ingestion, very fast ingestion, but when you really try to load millions of rows per second, most of the databases will get it as a big challenge. Okay, and how difficult it will be to ingest this? It is actually very simple. You create pipeline, you see the syntax here, and behind the scenes, the leaf nodes will connect to the Kafka partitions and will pull the data. The configuration is really simple. Okay. So a bit more use cases, just a few. Let's see, okay, a few use cases. So it is not very, very native solution for dashboards. Okay, for example, you have dashboards, it can be legacy dashboards on Oracle, it can be newer dashboards or something else, but this can be a very nice solution for dashboards. What can be problem with dashboards? In modern architecture, as Rob has mentioned, most probably you will have many types of databases involved. You will have a document store, and you will have some column store like here, Snowflake, and just some regular RDBMS like MySQL, and some others. And the data will be spread in all those databases. Now the organization usually wants to see like one picture. What's going on? How many sales did they have today? How many events? What is the relation between this data? And it becomes very, very complex. And actually, once every one of you who have used like many databases in the same system, you probably have experienced this. It is very difficult to get to a single source of truth. and it is very difficult to get some reports on top of all this salad, let's call it like this. And once the traditional approach is to build like ETL from those database to some sort of data warehouse, and then to do reports on the data warehouse. But then every change in the small database, you need to change the ETL. So it becomes a headache and plenty of work to manage it. Another point, which is actually another tip which I can tell about if you work with many databases. Another problem is usually they get out of sync. So you load database, you load the data in a different way to different databases. And after a month, 2 months, a year, you suddenly pay attention, there is a different data. There is event in one database, but it does not exist in another database. And there is inconsistency in data. And it always happens. Like, probably don't matter how you do it with several databases, you will always have inconsistencies. And there are ways to solve it, but it is complex. It is complex. So the solution here is that single store can suggest is very simple solution to put one solution for all the different workloads. Okay, because it can work with key value, it can work with it can work in any scale with trillions of rows, with analytics, without analytics, with transactions, with whatever you want, almost with whatever you want. Okay, so in this case, you have one data in one place. The data is consistent. There are no discrepancies, and then you can run reports on top of it, reports or whatever analytics. Okay, some feedback from customers. This is just customers, like it can you can have a really real-time dashboards, freshness of 30 seconds for dashboards for like very recent data. It can be even smaller than it. It can come to a few seconds, the freshness, big scale and speed, etc. Okay, just let's talk 3 more things and then we will jump to demo. There is a nice Spark connector to work Spark with single store if you wish. There is a cluster-to-cluster replication between different regions if you wish. There is a geospatial, which is actually very simple. The geodata is first-class citizen. You have plenty of geospatial objects and functions, and also geo indexes for fast geo operations. Okay. Okay, the last one. So who are the customers who are using single store? So in the world, there are many big customers like Samsung, Comcast, Uber, of course, Sony, Cisco, and many others with single store. In Israel, our customers, Monday.com, Playtika, Kensho, Clicktail, Windows, actually many, Iron Source, Fiverr, and we have about several new customers each month. So it's growing. Okay, I would like to show a small demo, not something big, and then we will conclude with questions and answers. Okay, so give me 1 sec to prepare for it. Okay, I think I'm ready. We will do like 5 to 10 minutes. So let's stop the presentation and do the screen share. Screen share? Maybe this one? Screen share. Okay. Oh, this is interesting. Infinity. Okay, I suppose you can see my screen. Okay. So here is a small single store cluster, which we installed in Amazon. We have here 3 nodes. This is a dashboard, which comes with the product. So we have 3 nodes, 1 aggregator node and 2 leaf nodes. The aggregator node is 4 cores and 16 gigabytes of memory. The leaf nodes are 16 cores and 64 gigabytes of memory. Okay, so for this installation, it's even with a free license. There is a free license for these sites. We can see the databases. We have created a demo databases, and in a demo database, we have some tables. Those tables are column store, and this is the table, application events. We can see there is a 13 billion events in this table, and it has a very good compression, 95% compression in this case. Okay, so inside the table, we can see what are my columns, how much the columns are use the disk space, the compression per each column, and etc. The SQL definition, which defines the table. And you can see that it's actually similar to MySQL, but not exactly similar. There are syntax, some additions using clustered column store, and there is a sorting inside, and there are the hash indexes, which are not present in MySQL. Okay, let's run some queries. First of all, let's see. First of all, I have to mention that the queries in MemSQL are compiled, which means that the first time you run it, it compiles in the background, and it compiles it to LLVM code, which is a sort of very near to machine level code. And the second time you will run the query, it will be faster. Even if you run it with different parameters. Okay, the compilation is without parameters. It will put your parameters into the compiled query. Okay, so this is one of the reasons why it can achieve a very high query throughput of thousands of queries per second. But on the other hand, there is no query cache. So for example, if I run this query several times, the result is not cached. It's always running the queries. If you want to build cache, it's need to build on top of it. This tool is actually adding about 100 milliseconds to the results because of the web UI interface. So in reality, this time is shorter. So let's take some aggregative query. We will take some query from this big table. We will filter to account. Account has actually many rows we will see, and we will group by user ID, application, and do some ordering on top of it. Oops, the second. We can run it. So it's like 200 milliseconds per this query. This query was on 13 billion events. And in this query, it did here plenty of work for one account. If we put another account, let's try. I'd like to do something like this. Okay. Because this data was not hot, it came to disk. It was a bit longer, but then the Linux buffer cache eventually will have most of the data in the Linux buffer cache. Okay. Next, there is another example, which is filtering by bigger group. Okay, here this query is filtering by something which is not very big. This group is significantly bigger. Similar query. So we see here, for example, for each application, the usage and how many records was in table after filtering for this usage. So here we already have millions in total, millions of rows which were aggregated. It scanned billions of rows. After filtering, it remains many millions of rows, aggregated everything. And it is still like a fast time, 300 milliseconds in this case, on a small cluster. And this is a huge account, really huge. If you run on it, it's a little bit longer. Here it's like tens of millions rows in total, which it aggregated after filtering. I want to show you one more query. Okay, this just a second. Sorry. This is something interesting. Okay. So this query, you can say, okay, the aggregation was fast, but what about joins? So here we join the application events with application properties, and application properties is not a small table. Let's see. So this is actually also not a small table to join. We have here 263 million rows. So we join between this table with billion rows, with this table of 263 million rows, and we do in the end some aggregation and summing, and still you can see that it is very fast. Okay. Now I want to show you something interesting inside. If, for example, we want to see what actually took the time, okay, what took the time, we can, there is a very nice query profiling here, which shows you, okay, during the query execution, this is very beautiful, where my time was spent. And I see, okay, my time was spent here on this column scan, and actually it scanned 88 segments, skipped of this small amount of segments. And on each step here, I have statistics. And then you can think if you want to improve it in some way, to resegment it or etc. Okay, very nice graphical plans. I think that we are about the time to finish and to leave some time to questions. So just a second. Okay. Good. So chat. Let's see if you have questions. Let's start from the end. Okay, presentation and etc. Okay, so guys, if you have some more questions, it's a good time. Let's see, maybe something was left here. Meanwhile, while we are looking for questions, I would like also to tell when not to use single store, okay? Because we said that it's actually good for many things, but when it's not so good to use it, I think it's not efficient solution for a place where you don't need fast queries or concurrent queries. So for example, if you have petabytes of data and you have some batch jobs, it's better to do it just to put the data on S3, Parquet format, partition, then to run Presto queries. It will be good enough and cheaper. So if you have like a big, heavy queries, heavy job operations, which doesn't really require from you a fast response time, then it is a less efficient use case for single store. Okay, there is a question here, Rob. I think it's better for you. What is the most of microservices used in the same data model? If most, okay.
That is a great question. What if my microservices use the same data model? It sounds like they might be the same microservice. If we draw our microservices around pieces of functionality and those pieces of functionality happen to be exactly the same, maybe they're the same microservice. As we start to separate them out, maybe one of them is computing things and one of them is storing things. And so we might separate our microservices that way. Not to say that a data tier should be a separate microservice from a computation tier. But ultimately, if your entire system shares in the same data model, it sounds like you don't have microservices. Rather, you have a distributed monolith.
Just okay, good. Just to add from what I've seen, sometimes people put a microservice, which is sort of the data access layer, which can serve other microservices as also an option, and then you always go to that point, and several microservices can consume it as an alternative, also another option.
Yeah. Our first stop in microservices usually is to take that lasagna architecture where we have each of those tiers and we say, okay, so my data access tier is my microservice and my business tier is my microservice and my UI tier is my microservice. And the hard part is those really aren't functionally, I'm muted. Thank you. Am I muted?
No.
No, those aren't functionally distinct. Rather, let's create microservices that are vertical so that we can say, here's all of the pieces associated with that microservice. And building those vertical slices might be a better indication of a good microservice architecture. It takes a while, though, to get comfortable with different microservices. So I understand, you know, the first stop, my microservices were awful. I like this question. Roma asks, my main concern regarding single store is that the data is stored on the leaves and not in object storage. So as we accumulate data, costs will grow rapidly. How to mitigate that? Good question. One of the things that we're working on with single store, now universal storage, is creating a mechanism where we can share storage across leaves and where we can persist row store data into durable memory, durable disk, and cache column store data to make them really efficient. So the short answer is there is a lot of stuff coming in this arena, and it is going to be really cool. In the medium term, as you're looking at this, I would argue that storing the data in the leaves is actually better because we can have each leaf responsible for its own separate data set. We can scale horizontally to get really massive scale. If all of the data was stored in blob storage, that would become the bottleneck in your storage. And all of the machines in front of it would just be caching and computation. Great question, though. Thank you for your thought.
Okay, so I see here more questions. So there is a question from Itzhak. What is the hardware when ingesting 10 million rows per second? So what I've seen ingesting 3 million rows per second, not 10. For 3 million rows per second, you're using 8 machines, each one with 32 cores. 8 machines with 32 cores. For 10 million, you need to multiply it by 3. 3 and a bit. Okay, so by the way, it's linearly scalable. You put more hardware, it becomes faster. Okay, there is a question from Roma. If we require a large OLTP store, does it mean that your single store solution will require a lot of memory, lots of instances in order to support that? Okay, it depends. It depends how much of the data is hot and how much of the data is changed in the last, let's say, in the last few minutes. Okay, if every few minutes you change a lot of data, then you will need more memory. If you change data, but you change like in a minute, you change less than 1% of the data, then you will not keep this data in memory because the changes are flashed from memory to disk very fast. It's a matter of several seconds or minutes. Okay, so you don't have.
You can do thousands of transactions.
Okay.
Edward asked a really good question. What infrastructure requirement does single store managed solution have? Do we have to be on a cloud vendor? Can we use OpenStack, K8s, or bare metal? That is a great question. The cool part about single store's managed solution is you don't need to do anything. You just get a database connection string and you connect to that from wherever you are. If you happen to be in the cloud, maybe you'll have less data latency, but you can pick the cloud that you want to choose as you spin up your managed service. Now, we also offer self-managed solutions where you can deploy that anywhere. K8s, OpenStack, virtual machines, containers. You can choose where you want to install single store at that point, and you can deploy it right alongside your application. If you get tired of managing your data store and you want to leave that management with single store, flip over to managed service and you have exactly the same database engine behind the scenes. All of the same mechanisms that you've come to love with really fast ingestion and no locking is available equally in managed service, and in the self-managed product you can install anywhere.
Okay, so I'll take one question of Rui. So when using single store DB, no need to create materialized view for quick snapshot of data. Is it true or false? So in many cases it is true, but the correct answer depends. Okay, so if your query is really scanning trillions of rows and if you do it thousands of times per second, then it is good to create materialized view. But in general, the need for those things is significantly less. You almost don't need to do it. In some cases, you still need to do it in order to reduce number of computation. This is regarding this one. And there is another question by Rui. Can we use this solution to store application events? Yes, it's classical for any events. It's classical for application events, networking events, IoT events, definitely.
Yeah, single store is great for time series data like application events. And one of the things that's a really elegant solution, single store uses a single store database to track its own monitoring. And so as you export your monitoring events from a single store database, you can choose to replicate those in the same or a different single store cluster, or you can expose them as a Prometheus sync. Single store is great for time series, and application events is no exception.
Okay, so let's take another question. How is a single store with parsing serving JSONs? I can understand it in different ways, but let's try to, what if the data is coming as JSON and we need to parse to ingest it? This is not a problem. When I talked about ingestion of 3 million rows per second, the data was coming as JSONs from Kafka. Okay, when the JSON is inside the database, it's actually stored inside the database in Parquet format in order not to parse it every time. It's not a regular Parquet. It's inside the column, but behind the scenes, it's a Parquet for JSONs. Okay, let's see more
And you can choose to index your JSON column, pulling out specific data if you'd like, to make access to that particular piece of that JSON really, really fast. So as you ingest it, you may choose to denormalize it and store it as a regular relational table, or you may choose to stick it inside of a JSON column. Either works just fine. If you choose to put it inside of a JSON column, you can choose to index certain fields in that JSON, and they will respond to joins and queries just as fast as any other relational column.
Very good point. Very good point. Okay. So there is a question here. In which cases Vertica is superior to single store? I think it will be mostly about the pricing. They have different pricing models, and then you can check which will be more efficient. But in general, from my experience with both of them, the engine of single store is significantly stronger. Okay. Let's see.
Yuval asked, which hybrid DB do you recommend? Are they stable and production ready? I guess the short version is single store is a great hybrid database that can work in lots of workloads. And so we'd love for you to give that one a try.
Okay, good. I like here a comment. You are two twins. Robert, you and me. There is some similarity. Okay. Let's see.
Presto connector.
Presto connector. Presto connector, from what I know, there is a Presto to MySQL connector, which will work. It will work with one thread. It's not like multi-threaded connector. It will work. How efficient it will be needs to be checked. If it will be very fast or not, needs to be checked.
We do have native connectors from Kafka and from Spark into single store, and we're building lots more connectors. So I'm not sure about a Presto connector, a native single store branded Presto connector, but you can, if you can do a query in Spark, grab that Presto data and stick it into single store really, really quickly, either with a pipeline or just with a native Spark module.
Yeah. The connector to Spark is very efficient. It goes directly to leaf nodes by passing the aggregators, and it's completely parallel, doing both reads and writes in parallel. So it's very efficient, the Spark connector. I think
and
that
the Spark connector version 3 is ever so much faster than the version 2 one, adding a whole lot more scalability and performance. And we're also working on a Spark connector that will work with Spark 3 as well. The Spark connector, by the way, is completely open source.
Good. Okay, I see here another question which I think I have missed. What infrastructure requirement does single store managed solution? Do we have to be in the cloud then? KTS. Maybe we answered it. It's like if you are going, you can deploy on any one of those. You have a Kubernetes operator, and then you just deploy on top of Kubernetes. And the Kubernetes can be on cloud, on premise, whatever, wherever you want. You can also deploy without the Kubernetes in the similar way like you deploy Vertica or Presto, etc. And there is a managed solution. The managed solution is something different. It's like a BigQuery. Okay, it's like something that you get as a service. Okay, so you don't need to create clusters and to like it's managed by in the infrastructure of the vendor. It can be near to you. It can be like if you're sitting in Amazon, it will be in Amazon in your region, etc. in Azure in your region, or Google Cloud in your region. This is about deployments.
If you're consuming it at your in your private data center, the managed service still, you can consume it from anywhere. If you happen to have your application in Google Cloud, AWS, or Azure, then that will remove the additional latency. But the beauty of the managed service is that it takes care of backup and deployment, authentication, all of the pieces that you don't want to have to worry about. All of that is taken care of in the managed service.
Okay, I see here a new question. I meant the other way, connect single score from Presto.
Itzik.
So if you, it's a question from Itzik. So if you want to connect to Presto from single store, I don't see a way to do it. Not at this stage. I don't think it is the right thing to do because single store is built as a very fast database, and going to Presto and to Presto sources might take some time. So from single store, you are not connecting to Presto. At this stage, there is no connector. From Presto, there is a connector to single store, but single-threaded connector. So if you have some other
questions. And the beauty of that with any application and framework is that it is just the MySQL connector. So if you have a MySQL connector or a MariaDB connector from whatever framework you're working in, then you can use that to connect to single store. At the point where we have a native connector, you might get a little bit more performance, but you can definitely use single store for all of your applications just by using a MariaDB or a MySQL connector.
Okay. I think it's good time. I don't see new questions, so I think we will conclude here, right? So Golan is here also. You can say hi, Golan.
I will leave my. Yeah, first of all, thank you very much, Ilya and Rob. I think it was amazing and very teaching and very nice, and I think I learned a lot from it. And we will share the recording and the presentations. You will get it. Everyone that was subscribed to this session, even those who didn't attend, will get it. And we will also put it in our website, and Rob also put it in his website. So, and if you want, you can send me an email. I will put my email here, and you are welcome to ask any question or demo or presentations or more questions.
I just want to say thank you very much to Rob. It was so amazing to be with you in a team doing this. Thank you.
After the Corona, we
Yes,
will.
I agree. It's been so much
Israel.
fun getting to present here in Israel today. Thank you.
Bring you to Israel to do a physical meetup, a real meetup.
Most definitely.
So great. Thank you very much, everyone. It was a pleasure. Bye. See you in the next meetup.
Thank you, everyone.
End call.